All right, welcome to your final exam review. So, a large portion of the non programming questions will revolve around fourth quarter material, but there will be material from quarters one, two, and three, mostly focusing on the major topics from quarters one, two, and three. So, that includes things like conversions, circuit diagrams, assembly language, but like the main topics from quarters one, two, and three, and then more of the details from quarter four. All right. So if we take a look at this first question, it says, what is the output of the neuron net below if the inputs to the leftmost layer of the neurons are 1, 1, 0, 1, 1, 1, as shown? The synapse weights are shown along with each neuron's threshold. Right? So remember, for this to output a 1, we have to exceed the threshold. If we don't exceed the threshold, we output a 0. So if we exceed the threshold, we get a 1. If we are less than or equal to, we get a 0. All right. So if we look at this first one, we have a weight of 2, a weight of -1. Those are both receiving 1 input. So it becomes 1 times 2 plus 1 times -1, which gives us a 1. 1 does not exceed this threshold. So this first one is going to output a 0. All right. On this next one, we have 0 times -1 plus 1 times 2. All right. 0 plus 2 is 2. This time we are exceeding the threshold, so we output a 1. All right. We only ever output ones or zeros. This just determines whether we exceed or fail to exceed the threshold. So it's not like we output a 2 or anything like that. And then this one down here, we have 1 times 1 plus 1 times 2 for a total of 3. Again, we're exceeding the threshold, so that would be a 1. All right. Now that we know the outputs from the first layer, those outputs become the input to the second layer. So now I have 0 times -1 plus 1 times 2 plus 1 times 1 for a total of 3. All right, that exceeds the threshold value of 2 here. So the final output is going to be a 1. All right. So again, it's just going through the different weighted averages, looking at the inputs, generating the outputs, and then feeding those outputs into the next layer. All right. But understanding how these work, understanding how they're connected, understanding that the inputs are always ones and zeros. It's the weights and the thresholds that can have, larger values than that. Okay, but the inputs and the outputs are always ones and zeros. All right, let's take a look at the next one. So consider the main memory configuration below where the gray partitions are currently in use. Suppose 3 more processes start running in this order, A, B, C. Show where A, B, and C will be placed using the best fit algorithm. All right, so we talked about memory management in the operating systems unit. You have to understand these 3 algorithms and where they place programs, according to their rules. So best fit means you're going to use the smallest available space. So if we look at the very start, this one is size 40. This one is size 30. And this one is size 50. So if we're placing A, we want to use the smallest available space that will still work. So that would be this size 30 right here. And we would put A right here. All right, so A would go right there. It would use up 20 megabytes, and we'd still have 10 megabytes left over as empty space right there. All right, but that would be program A. All right, next would come program B. So program B requires 30 megabytes, and we're still trying to find the smallest space that will still fit that. So we've got 40 megabytes here, we've got 10 megabytes here, we've got 50 megabytes here. So it'll fit in these two spaces, but we use the smaller of the two, and that means that B is going to go right here. So this will be B, and it will use up the 30 megabytes there. All right, and then last but not least, that leaves us C, which is 10 megabytes. So this one is size 10, this one is size 10, this one is size 50. So there's actually two places where it fits exactly. And when that's the case, we usually just use the first one sequentially. All right, so here we're just going to place C right here because it's the first one kind of sequentially in the memory. So there's C, and it can go there. All right, if you placed it here, that would be fine. I would still be okay with that, but generally, if there's two spaces the same exact size, you're just going to put it in the first one that fits. Okay, so there we have best fit algorithm. Again, we use the smallest available space. That fits a program. Right? If it's too small, then we can't use it because it won't fit it. But as long as it fits it, we want the smallest possible one. All right. Part B, same thing, except we're using worst fit. All right, so worst fit is using the largest available space that fits a program. Okay. So again, A is still 20, B is still 30, C is 10. We're leaving that all the same. But now instead of finding the smallest available space, we're using the largest available space. So again, this one's 40, this one's 30, this one over here is 50. So when we're placing A, we're going to place it in the 50 spot here because it's the largest available. All right, so A would go in right here. Now we get to B, which is size 30. And again, we're looking for the largest available space. So we have 40 here, we have 30 here, we have 30 here. So even though it would fit perfectly into either one of these spots, we use the largest available space, which means that B is going to get placed right here. And we'll have that 10 left over. And then again, now we're placing C. And even though it would fit perfectly in here, we don't use that spot. We use the largest available spot. Again, this one is size 30. This one is also size 30. All right, they're both size 30. So again, in theory, you could place it in either, but we're going to use the first one that works. So we're going to place C right inside of here. All right, but again, both of these were size 30, so equally worst fit, if you want to think of it that way. All right. And then last but not least, we've got the first fit algorithm, which is basically use the first available space that fits the program. Okay. So we've got A, which is size 20. There's room for it in this very first spot. So we just put it right there. There's A. All right. Then we get to B, which is size 30. Not enough room to put it there, but there is enough room to put it in here. It'll actually fit perfectly. So we'll put B in here, and that'll use up all 30. And then C is only 10, so we have room for C right here. Again, that's the first available space. So C would just go right next to A in there. All right. So again, knowing how to do this memory allocation piece, knowing the difference between best fit, worst fit, and first fit, and being able to basically assign programs to different sections of the memory based on the appropriate rule. But something from this quarter, something you should expect to see on your final exam. All right, now the other thing that we did in the operating systems unit, which you should expect to see on your final exam, is the process scheduling. So this says, suppose processes A, B, C, and D are waiting in the order listed to use the CPU for the amount of time indicated. At what time will process D finish using the CPU if the shortest job next scheduling algorithm is used? All right. So generally the way we do this is we set up a Gantt chart. So if we're doing shortest job next, B would go first, and B would go from 0 to 10. That would be followed by D, which would go from 10 to 50. That would be followed by A, which would go from 50 to 110. And then that would be followed by C, which would go from 110 to 200. So this question is specifically asking about process D. What time will it finish? We can then look at our chart and say very easily, oh, it's going to finish at time 50. B says, at what time will process D finish if the first come, first serve scheduling algorithm is used? So that just means we do them in the order they arrive. So A would go first, 0 to 60. B would come next, 60 to 70. C would come after that, which brings us to 160. And then D would bring up the rear, which brings us to 200. So if we used first come, first serve, since D arrived last, it would have to wait the full time there, and it wouldn't finish until 200. Now, C says, at what time will process D finish if round robin scheduling is used using a time slice of 20? All right. So that's where we say, all right, each process gets 20 cycles. And then once those 20 cycles are up, we move on to the next one. So we would start and say, okay, we're going to do a little bit of A, and A is going to get from 0 to 20. Right? It's not done yet, but all it gets is 20. So if we kind of use this as our tally mark, we've brought it down to 40. Then B gets to go. B doesn't need the full 20, it only needs 10, so it only uses what it needs. All right, so that would go from 20 to 30, and then this process has finished. Then C would get to go. C would use its full 20 cycles that it's allotted. So now we're at 30 to 50. And this is down to 70. And then D would get its first shot. It's not done yet, but it would get a turn, and it would go from 50 to 70. And now it only has 20 cycles left to finish. All right. But it doesn't get to finish. We rotate back around. So now A gets another turn and goes from 70 to 90. B has already finished, so we don't have to worry about B anymore. C gets its turn and goes from 90 to 110. All right, now there's 50 cycles left on C. All right, D gets its turn again. It's going to go to 130, and that's enough to finish. All right, so D is going to finish at 130, but I'm going to keep going and kind of finish this off so we can see where everything ends up. All right, so D is going to finish, then A gets a turn and goes from 130 to 150. All right, and that's enough to finish A. And then at this point, the only thing that's left is C. So C would just keep going and finish at 200 because there's nothing else that it needs to share with it at any point. So it'll just keep the processor until it finishes because it's not waiting for anything else to go. All right, so this would be sort of the round robin approach. And this one specifically asks when D finishes. So the answer to that would be 130. All right. Now, the reason I did the whole chart is the next question says, what will the average turnaround time for the processes be if round robin scheduling is used with a time slice of 20? All right. So we basically have to look and see when does each process finish. All right. So process A finished at 150. Process C finished at 200. Process D finished at 130. And process B finished up here at timestamp 30. So we can just take those 30 plus 130 plus 150 plus 200. And we need to just divide that all by 4. Okay, so let's see, that's 350, that's 450, 480. So that gives us 510 divided by 4, which should be, I believe, 127.5. So that would be our average turnaround time for this situation. All right. But again, knowing the difference between the algorithms, knowing how to set up these Gantt charts, knowing how to calculate, an average turnaround time. All right. And you're basically just looking for when the process is finished. You find all the finishing times, you add them together, you divide by, however many there were. You just take the average. All right. But something that we did this quarter, something you should expect to see on your final exam. All right. Next. Suppose when the assembly language program below on the left starts running, it gets put into main memory that begins at 10/20/25 or 10/22/25. For this program to run correctly, it's assigned partition. The logical memory addresses, which are these over here, need to be converted to physical memory addresses. Mark the address changes that need to be made to the program in main memory so it will run correctly in its partition. All right, so when the programmer wrote the program, they said load 5, compare 6, increment 5, jump 0. But when it actually gets loaded into memory, it's not likely to be loaded into memory location 0 because memory location 0 is probably being used by the operating system or something else. Right? It's going to get loaded wherever it has room, according to whatever memory management algorithm we're using. And then these addresses have to be adjusted. So load 5 is basically saying, hey, load something 5 addresses higher than our starting address. So if our starting address is 1025, we're going to load something 5 higher, and this is going to become 10260. Right? If we're comparing 6, we're comparing 6 higher from our starting point. So this becomes 10261. This is another 5. So this becomes 10260 again. And then this last one is jump 0. So that's just going to be our starting address. And our starting address, we were told, was 10255. All right. So these problems aren't difficult. You just have to understand what they're asking you to do. And then at that point, you're just kind of taking this base address. This is your starting point. And it's basically just the starting point plus the logical address. All right. And these right here are the logical addresses. All right. So once you know your starting point, once you know your logical addresses, you just add those together for each instruction to get your physical memory addresses. Okay. Now, let's take a step back and look at some of the problems from earlier in the year. Now, the very first thing we did in this course was conversion. So we learned how to convert from binary to decimal. We learned how to convert from decimal to binary. And then we also looked at things like hexadecimal and octal and things like that. So all of those are fair game on the final. So let's do a few of these just to kind of review how it works. So this one says, convert 56 in base 10 to binary. So this is a 56 in base 10. We want to switch it over to 56 in binary. All right. So there's two approaches. There's the remainder algorithm and there's the greedy algorithm. All right. So the way the greedy algorithm works is you're basically doing kind of repeated subtraction. So we can kind of set this up and say, all right, with binary, there's the 1 spot, there's the 2 spot, there's the 4 spot, there's the 8 spot, there's the 16 spot, there's the 32 spot, there's the 64 spot, and I'm not going to go any higher because 56 is the number we're trying to represent, so there's no point. All right, so if I'm using the greedy algorithm, I say to myself, okay, 32 is less than 56, so I can have a 1 here. All right, but once I put the 1 there, I now only have 24 left over to get up to 56. So that means I still have room to use the 16 spot. Once I use the 16 spot, I only have 8 left over. All right. Well, 8 is one of my spots, so I can put the 1 there. I now have nothing left over, so the rest of these have to be 0. So 56 in binary is 1, 1, 1, 0, 0, 0. All right, that's the greedy algorithm where you basically find the biggest number that'll work, you subtract it away, then you find the next biggest number that'll work, next biggest number, so on and so forth. All right, the other way to do it is the remainder approach, which is where we say, okay, 56 divided by 2. All right, that goes in 28 times with a remainder of 0. 28 divided by 2 goes in 14 times with a remainder of 0. 14 divided by 2 goes in 7 times with a remainder of 0. 7 divided by 2 goes in 3 times with a remainder of 1. This goes in 1 time with a remainder of 1. And this goes in 0 times with a remainder of 1. When you eventually get to something that goes in 0 times, that's when you know to stop. And then you read your answer top to bottom. All right, so my answer would be 1, 1, 1, 0, 0, 0. 1, 1, 1, 0, 0, 0. And you'll notice that I got the same answer regardless of the way I did it. All right, so you're not required to do it one way or the other. You can either do it the kind of addition subtraction way, or you can do it the division way. Now, what I will say is this way is probably more work, but you're less likely to make a mistake because it's very clear what's happening, right? This one is a little easier because it's just kind of automatic, but it's easier to like goof up one of these divisions and not find your mistake. All right. So, it's up to you which one you choose. I think this one is less error prone, but takes longer. I think this one's quicker, but you're more likely to make a mistake. So on a final exam, maybe you do it both ways and make sure you get the same answer. But I leave that up to you. All right, next one says convert 60 in base 10 to hexadecimal. All right. So again, there's a couple of ways we can do this. All right. One way is the same division approach we just used. All right. Only instead of dividing by 2, we'll be dividing by 16 because it's hexadecimal. So we can say 60 divided by 16. All right. This is going to go in 3 times with a remainder of 12. All right. 3 times 6 is 48. 48 has 12 left over with this 60 here. Okay. I can then divide by 16 again. It's going to go in 0 times, which tells me to stop. And the remainder is going to be 3. All right, so when I get that 0, that's what's telling me to stop. Now this 12, I don't write 312. I have to remember that it goes 0, 1, 2, 3, whoops. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. So A is 10, B is 11, C is 12. So this 12 is really a C, and my final answer, because I go top to bottom, would be 3C. Right? The other way to do base 10 to hexadecimal is to first convert to binary. All right. Now, if I'm going to convert this to binary, I'm going to kind of take a shortcut and use what I did up here. All right. So 56 is 111000. If I want to go up to 60, that just means I need 4 more. So in binary, this is 111100. All right. Now, why does that help me? All right. It helps me because 4 binary digits equals 1 hexadecimal digit. So I can divide this into groups of 4 and just put leading zeros there. And then I just have to convert this into the individual hexadecimal digits. So I can say to myself, all right, this is 12, which corresponds to C. This is just 3. So then this is my final answer of 3C. So again, it's up to you how you do it. I leave that to you. You can either do the division way where you're dividing by 16, and then it works just like this, where you're focusing on the remainders, or you can first go to binary and then remember that 4 binary digits equals 1 hexadecimal. All right. Up to you how you do it, but both of those techniques are valid. 7, convert 1AB in hexadecimal to base 10. All right. So when we're converting to base 10, that's usually where we're multiplying things out. Right. And what we have to remember that each of these is to a power of 16. So B is really 11 times 16 to the 0 power. A, because it's in the next slot over, is really 10 times 16 to the first power. And this 1, which is 2 spots over, is really 1 times 16 squared. Okay, so 16 squared is 256. So 1 times 256 is just 256. 16 to the first is obviously 16. So 10 times 16 is 160. And then 11 times 16 to the 0 power is just 11 times 1. So that's 11. And then we would just add those together. All right, we're adding these together. All right, and when we add those together, we're going to get, let's see, 300, 416, 427. All right, so our final answer there would be 427. All right, 8 says convert 11011 in binary to base 10. All right, so we're going to do the same thing we just did, only instead of using powers of 16, we're going to use powers of 2. So this is 1 times 2 to the 0 power. This is 1 times 2 to the first power. This is 0 times 2 to the second power. 1 times 2 to the third power. And 1 times 2 to the 4th power. All right. So this one's just 1 times 1. This one's 1 times 2. This one's 0 times 4. This one's 1 times 8. And this one is 1 times 16. So when we add these all together, or 26, we're going to get 27. All right. Now these, I think you can also just kind of do sort of the reverse way that I did the greedy algorithm and just say, okay, if this is my number, I know this is my 1 spot. I know this is my 2 spot. I know this is my 4 spot. This is my 8 spot. This is my 16 spot. And just say, okay, this one's off, so I ignore it. It's got a 0. And then just add these other numbers together. And either way, you get to the 27 there. So however you do it is fine. But because binary is just on, off, sometimes it's easier to just look at it this way than actually go through and write out the multiplication. On this one, you kind of need to write out the multiplication because it's not simply whether the spot is on or off. It's, does the spot have a 10 in it? Does the spot have an 11 in it? Does the spot have a 4 in it? So it doesn't work the same way, but it does. We can use it this way for like the binary one. All right, number 9. Convert 273 in octal to base 10. All right. Now this has nothing to do with this problem, but since this is the first one that mentions octal, just like 4 binary digits is 1 hexadecimal, 3 binary digits equals 1 octal digit. All right. Again, doesn't really relate to this problem, but since I mentioned this up here, I wanted to mention this down here. So this one just says convert 273 in octal to base 10. So exactly what we just did, only now we're dealing with powers of 8. So it's going to be 3 times 8 to the 0 power. It's going to be 7 times 8 to the 1st power. It's going to be 2 times 8 to the 2nd power. All right. So effectively, that's going to give us, this is 64 times 2 is 128. Plus 7 times 8 is 56. Plus 3 times 1 is just 3. So let's see, that gets us up to 187, I believe. And that would be our final answer for that one. All right. So again, conversions are fair game. It could be base 10 to hexadecimal. It could be base 10 to octal. It could be binary to octal. It could be binary to hexadecimal. Any of those combinations. You should just be familiar with how to move between the different number systems. All right. And then the other question that we saw a lot in the first quarter was something like this. What is the smallest and largest sign magnitude value you can represent in 9 bits? Express your answer both in binary and base 10. All right. So sign magnitude is where you use 1 bit for the sign. And basically a 1 is negative and a 0 is positive, which means the largest possible number you could represent starts with a 0 to represent that it's positive, and then it's going to be followed by 8 ones. All right, why 8? Because it said we had 9 bits in total. The smallest possible number is going to be a 1, which represents the negative, followed by, again, 8 ones. All right, so this is what's telling me it's negative. This is what's telling me it's positive. This is the actual number, right? This part is the actual number. All right. So what's the largest thing that I can represent? Well, I've got to turn these 8 ones into a decimal value. All right. Now there's a couple ways to do that. You could just manually, go through it like we did up here. So it would basically be 1 plus 2, plus 4, plus 8, plus 16, plus 32, plus 64, plus 128. Right? And if we do that, that works out to 255. Now, the other way to get to 255 is to say, okay, I've got 8 bits, so that's 2 to the 8th, gives me 256 different numbers, and those 256 different numbers are from 0 to 255. And then the same thing down here. If I've got 8 bits, 2 to the 8th is 256, but we start at 0, so from 0 to 256 is going to be negative 255. All right, so my range is from negative 255 to positive 255. That's my smallest number. That's my largest number. This question doesn't ask, but if I wanted to know how many different numbers I could actually represent, all right, the number of different numbers is going to be 511. Why 511? Because I have duplicate zeros, all right? It's not 512 because I wasted space because I have duplicate zeros. All right, I have a positive and a negative 0 when I use this sign magnitude notation. So I only get 511 different numbers. I get from 255 to negative 255, but because I'm counting 0 twice, I only get 511 different numbers. Now again, 2 to the 9th is 512, but then I'm subtracting 1 off that because I have the double 0 that I'm counting there. Okay. All right, that's the downside of sign magnitude, is that you lose a number there because you've got the positive and negative 0. All right, but again, all this stuff from sort of the first quarter that is fair game on your final exam. All right, next. Using the sum of products circuit construction algorithm, show the Boolean expression for the truth table. Show your work at each step of the algorithm. Draw a circuit that implements the functionality of kind of what's going on here. All right. So the first step is to sort of identify the rows that have a 1. So for us, that would be here, here, down here, and down here. Okay. Now we have to see what represents those. So this is A0, B0, C0. So we write that as A naught, B naught, C naught. This one is A0, B0, C1. So we write that as A naught, B naught, C. Here we have an A1, B0, C1. So that would be A, B naught, C. And then last but not least, we have ABC. So that would just be A, B, C. So those are the individual rows that give us a 1. The Boolean expression is just adding all of those together. So the final expression would just be A naught, B naught, C naught, plus A naught, B naught, C, plus A, B naught, C, plus A, B, C. You are under no obligation to try to simplify this. All right. I would recommend that you don't try to simplify it, because if you simplify it and make a mistake, you're going to lose points. If you simplify it and do it correctly, I'm not going to take away points, but I'm not going to give you extra points. So there's really no advantage to trying to simplify it. Just leave it in that form. All right. Next, it says draw a circuit that implements this gate that we just designed. All right. So again, the way that we kind of learned how to do this to sort of keep it neat is we start and we say, all right, here's A. Here's my line for A. And then I have a little wire that comes off. I send it through a NOT gate, and that's going to be my A NOT wire. Then I'm going to do the same thing for B. I'm going to have a B wire. I'm going to have another wire that comes down. And whoops, forgot to draw my triangle. But that's my B NOT wire. And then I'm going to do the same thing for C. All right. There's my triangle. There's my C NOT wire. All right, so now I have all of those. And I'm just going to tap them to sort of create the different gates that I need. So this first one is A NOT, B NOT, C NOT, all being ANDed together. So I'm going to draw a line right here. There's my A NOT. There's my B NOT. There's my C NOT. And they're all going into an AND gate. All right, put a little dot in there to show that it's an AND gate if you want. Then I'm going to do the same thing again. A NOT, B NOT, C NOT. Or sorry, just regular C this time. So A NOT, B NOT, and then C. So there's our next one. Again, those are feeding into my AND gate. Then I've got A, B NOT, C. So A, B NOT, and then C. Those are feeding into another AND gate. And then last but not least, I've got ABC. So A goes over, B goes over, C goes over. They're all feeding into an AND gate. And then all of those are being ORed together. All right. Now you can draw it as like one big OR gate, or a lot of times like we try to want to limit it to like 3 into a single gate. So you could draw it like this, where I have like 3 going into an OR gate. And then I have this OR gate feeding into another OR gate with this one. Or you can draw it as one big one. I'm fine with either. Whether you cascade them or you draw it as one big one. The idea is that they're all being ORed together, right? And that would be the circuit diagram for this that I just came up with. All right. So again, sum of products algorithm, something we spent a lot of time with in the second quarter, something that you should be comfortable with, on this exam. All right. Last but not least, write a Boolean expression for the following circuit. All right. So we're going to take this circuit diagram and turn it into something that looks like this up top here. All right. So if we notice, we have 2 AND gates. We have 1 OR gate, and we have 2 NOT gates. So when I'm writing my expression, I should be expecting to have 1 addition, 2 multiplications, and 2 negations. So let's see what we have here. All right, we'll start with this one right here. So this first AND gate right here is just A and C. So I'm going to write this as A times C. All right, there's my first AND gate. That is being knotted. So I don't knot each one individually. I knot the whole thing. So there's the AC knot. Now this AC knot is going into an OR gate with B. So I've got AC knot plus B. All right, B is feeding into the OR gate. The other end of the OR gate is this AC knot that I just did. This whole thing, AC knot plus B, is then feeding into an AND gate. So this whole thing is being multiplied by not A. All right? So that would be my final expression. All right, there's the multiplication for this gate. There's the addition for this gate. There's the second multiplication for this gate. There's my first negation. There's my second negation. So every gate that I'm seeing in this picture, I can trace back to something in my Boolean expression. All right, so again, this is the sort of material that you need to be able to kind of reproduce on the exam. Now, on this, let's talk about what I focused on. All right, I focused on the material from this quarter because it was new. So neural nets, memory allocation, process scheduling, address binding. That's the new stuff. I focused on the really old stuff, conversions, circuit diagrams. Be aware that I didn't specifically cover in this, but you are still responsible for things like assembly language, converting from Python to assembly, converting from assembly to Python, and also those questions where you're kind of filling in the registers and saying, okay, after this command, here's what's in the registers. After this command, here's what's in the registers, and stuff like that. That should be a little fresher in your mind because it was just third quarter that we took that test, so it wasn't that long ago. And you are still responsible for that material. So even though it's not specifically covered in this video, it is on things like your topic sheet, it is on your practice exam, so you are responsible for those types of problems. On the final, I just didn't specifically cover it because it is a little fresher compared to some of this other stuff. All right, so I hope this was useful. Obviously, if you have any questions, let me know, and we will go from there. All right, have a great day.